This lesson is on potential energy. So far, the only kind of energy that we have talked about is kinetic energy, or energy of motion. But clearly there are other kinds of energy besides energy of motion, and one of those is potential energy. Potential energy is energy that an object has because of its position or configuration. And to illustrate what I mean by that, remember that our working definition of energy is the ability to do work, which is exerting a force over a certain distance on an object. Okay, and to see that an object's position can affect its energy, let's consider a bowling ball. Okay, here's a bowling ball sitting on the floor. You're not too worried about that. All right, here is a bowling ball that is on the shelf, and you're standing under that shelf. Okay, that bowling ball concerns you, but the one on the floor does not concern you. Why? Because neither bowling ball is moving, so neither one of them have kinetic energy, but you, of course, just intuitively understand that this bowling ball, the one on the shelf, if somebody nudges it, or somebody just maybe rattles the wall, then it could fall off the shelf. And even though it doesn't have any kinetic energy while it's on the shelf, it has the potential to have kinetic energy because of gravity. It will be accelerated by gravity if it falls off the shelf, and then it will have kinetic energy and has the possibility of doing work on your head. So there's something about the position of the bowling ball on the shelf that is different than the position of the bowling ball on the floor. And that difference, we would say, is due to potential energy. The location of the bowling ball on the shelf is one that gives it potential energy. The one on the floor does not have as much potential energy. In this case, the potential energy is due to gravity. There, of course, can be potential energy due to other things besides gravity. If you have, for example, a spring, and a spring that is not stretched out doesn't have as much energy as a spring that is stretched out. Okay, so we would say that this, the spring that's stretched out has more potential energy than the one that's not stretched out, because if you let go of the one that's stretched out, then it will have kinetic energy. You also can have potential energy because of electric charges. Everybody knows that like charges repel and unlike charges attract. So if I have a positive charge here and a negative charge over there, then if I hold them in place, they won't have any kinetic energy. But as soon as I let go of, for example, the negative charge, it will be attracted to the positive one, and it will have kinetic energy. So you can have, there are lots of different kinds of potential energy. The one that we are most interested in for the purposes of this class is gravitational potential energy, or potential energy that an object has because it is in an area where there's gravity. So let's talk a little bit more about that kind of potential energy. In fact, we'd like to be quantitative with it. So let's say gravitational potential energy, which we will give the symbol PE. is equal to the object's mass times gravity times h, where h is the height of the object. Okay, let's think about each of these three terms one at a time. First of all, the mass. That makes sense. If it's a ping pong ball on the shelf instead of a bowling ball, you're not going to be too concerned, even if it's right above your head. The strength of gravity is obviously important. If you were to drop a bowling ball on your head on the moon, it wouldn't hurt as bad as if you drop a bowling ball on your head on Earth, because gravity is stronger on Earth. And then the height. If you drop a bowling ball 1 inch onto your foot, that's not going to hurt as bad as if you drop the bowling ball 10 feet onto your foot. So each of those three terms affects how much potential energy an object has. By the way, I should point out something about this height, h here. If you're on the second floor of a building, say, like our classroom is on campus, the physics classroom, and we have a bowling ball up on the shelf, and here's the floor, but that's the second floor of the building, and the first floor is down here. So when I'm trying to figure out how much potential energy this bowling ball up on the shelf has, what height should I use? Should I use this one, which I'll call height number 1, the height off of the floor in the classroom? Should I use this height, which we'll call h2, the height from the bowling ball down to the ground floor? Or, for that matter, somebody might say, well, you know, campus is not at sea level. We're probably 2,000 or 3,000 feet above sea level at various places on campus. Maybe I actually should use some other height, you know, that's way down there. We'll call that h3, the height of the bowling ball above sea level. And then somebody else might say, well, how about the center of the Earth? Let's use that. So which one should we use? And the answer is, it doesn't matter. You can pick whatever height you like to be h equals 0. It's sort of like picking the origin of your coordinate system. You can pick anywhere you want to be x equals 0. You can pick anywhere you want to be h equals 0. The important thing is that once you've made a choice, you stick with it throughout the rest of your problem. Okay, so most of the time we will pick, if we're doing something in our classroom, most of the time we'll pick h equals 0 on the floor of our classroom. So that if we were working a problem with this bowling ball on the shelf, we would probably pick h1 as being the height of the bowling ball. Now, you may be wondering, well, that's kind of weird. You mean that I basically just get to decide how much energy my bowling ball has? And the answer is, well, sort of. You do get to decide how much potential energy your bowling ball has, but it turns out that whenever you're solving a problem, it's only differences in potential energy that end up mattering. So because you're only going to be considering differences in potential energy, you'll always be subtracting one potential energy from another, and the energy that you pick to be h equals 0 will always cancel out when you take that difference. So it ends up not mattering for the purposes of working the problem. Okay, well, speaking of working problems, what kind of problems can we solve using this idea of potential energy? Let's do that next. let's consider next the bowling ball hanging on a rope from the ceiling. And here's the floor. Okay, so let's say that we have the mass of the bowling ball is m. And I'm going to hold this bowling ball a distance of 1 meter above the floor. Okay. And if I let go of the bowling ball, then of course the bowling ball will start swinging like a pendulum. And it'll be going back and forth like that. Okay. Well, when I'm holding the bowling ball still 1 meter above the floor, my bowling ball has potential energy, but it doesn't have kinetic energy because it's not moving. Okay. But when I let it go, the bowling ball starts to move. And when the bowling ball gets, I'll say, about right here, halfway down to the ground, then it still has some potential energy because it's still above the floor, but it also has some kinetic energy because it's now moving. Well, the bowling ball will continue to speed up until it gets down to the bottom of its path. At that point, it has kinetic energy, but it doesn't have any potential energy, at least if I say h equals 0 down at the floor, which I will. But then what happens? Well, the bowling ball continues to swing like a pendulum, and it gets up here where it now has some potential energy again, and still some kinetic energy because it's still moving. And eventually it gets to be all the way up here to its highest point on the other side of its swing, at which point it's not moving at that moment, so it has no kinetic energy, but it has some potential energy again. As long as we're not losing any energy to air resistance or friction or anything like that, then the kinetic and the potential energy of the bowling ball must be conserved. Okay, so as long as we have no energy loss due to air resistance or friction, the total amount of kinetic energy plus potential energy of this bowling ball has to equal a constant. It's conserved. Total energy is conserved. So that's just a way of writing the law of conservation of energy. Or another way to write the same thing would be that if I know the kinetic energy plus the potential energy of the bowling ball at location 1, then that must be the same as the kinetic energy plus the potential energy at location 2. Okay, so we can actually use this to find the speed of the bowling ball at various points along its path without having to use any kinematic equations and without having to use Newton's laws. Let's do that. Let's figure out, for example, what is the kinetic energy of the ball when it has come down to the bottom, gone halfway back up. So this point right here, where the height is equal to 0.5 meters. Okay, I want to find the velocity of the bowling ball when it gets to that location if I release it from rest 1 meter above the ground. Okay, well, let's use this equation. We have the kinetic energy plus the potential energy of the ball at location 1, right here. That has to equal the kinetic energy plus the potential energy of the ball at location 2. right here? Well, on the left side of this equation, the kinetic energy at location 1 is 0 because I'm releasing the ball from rest. The potential energy at location 1 will be the mass of the ball times gravity times the height at location 1. The kinetic energy at location 2 is 1/2 mv squared, where v is v2, the speed at location 2, plus mg h2. Let's notice, by the way, that we have a mass in each term. We can divide both sides of the mass, or both sides of the equation by the mass, meaning that the mass cancels. Now let's fill in the numbers. G is 9.8 meters per second squared. H1, the height of the bowling ball at position 1, is 1 meter. 1/2 V2 squared, V2 is what we're looking for, plus 9.8 meters per second squared times H2, the height of the ball at location 2, which is 1/2 meter. Okay, 9.8 times 1 gives us 9.8 meters squared over seconds squared. That's equal to 1/2 V2 squared plus 9.8 times 1/2 is 4.9 meters squared per second squared. We now need to subtract 4.9 from both sides. So that gives us 9.8 minus 4.9 is also 4.9. So we have 4.9 meters squared per second squared. Equals, so I'm just trying to clear some room for myself here, equals 1/2 V2 squared. Let's multiply both sides by 2, giving us 9.8 meters squared per second squared equals V2 squared. If we take the square root of both sides, then we get that V2 is equal to the square root of 9.8. 9.8 square root is 3.13. So we have V2 equals 3.13, and that will be meters per second. All right. So notice that we were able to solve for the speed of that bowling ball, and we didn't even need to draw a free body diagram or anything on that bowling ball or use any kinematic equations. We simply used the conservation of kinetic and potential energy in order to solve the problem. You can use conservation of kinetic and potential energy as long as you're not losing energy to something like friction or air resistance. If you're losing energy to friction or air resistance, then you'll have to account for that somehow in the problem. Okay, let me ask you a question now to check your understanding. And let's say that we're at the water park, okay, and at this water park we have two water slides that are right next to each other. So you climb the tower, and up here at the top of the tower is the platform where you stand, where you're waiting in line, okay, and then we have two water slides. One is fairly steep, and the other one is more gradual. So so if we call the steep one water slide A, and the more gradual one water slide B, the question is that if you have two riders, one riding A and one riding B, and they both start from rest up here at the top of the water slide, which one will be going fastest when they reach the bottom of the water slide? Do you think it will be A, B, or do you think that they will both be going the same speed when they reach the bottom of the water slide? Pause the recording, think about this, come up with your own answer, make sure you understand your reasoning, okay, and then unpause. You get more out of this if you actually, if instead of just continuing on and listen to me explain the answer, you try and figure it out for yourself first. All right, well, if you're ready for the answer, the correct answer is C. They'll both be going the same speed when they reach the bottom. And that is because at the top, they both have the same potential energy when they start, right? They both start at the same height. They're both starting from rest, so they both have a speed equal to 0 when they're starting out. So their potential energy and their kinetic energy are both the same. Down at the bottom, they both have H equals 0. So there is no potential energy at the bottom. Well, since when they started, they had the same potential and kinetic energy, and when they end, they have the same potential energy, then when they end, they must also have the same kinetic energy and therefore the same speed. Now, that argument that I just gave you would be for the case where both of the people have the same mass. But even if they don't have the same mass, you get the same answer because remember in the previous problem with the bowling ball, the mass of the bowling ball canceled. So the mass actually doesn't matter. You get the same answer regardless of the mass. Okay, well, let me ask you a slightly different question. If I asked a slightly different question, which rider gets to the bottom first, then the answer would be A. Okay. So if you're saying, now wait a minute, if they both are going the same speed when they are at the top and they're going at the same speed when they get to the bottom, how is it that the rider of slide A gets there first? Well, all I said was that they're going the same speed here and they're going the same speed here. That doesn't tell us anything about what their speeds were halfway down. If you pick any point, let's say this point right here, then at this spot right here, B is not going as fast as A because A has fallen more. In other words, A has turned more of his potential energy into kinetic energy than B has. So A will be going faster at that point. A continues to go faster all the way down until A gets here. When A gets there, he's reached the bottom. He doesn't speed up anymore. He just goes his final speed the rest of the way down the water slide. Whereas B is still speeding up and hasn't matched the final speed of A until the very end, right here. Okay, so even though A and B both end at the same speed, for most of the trip, A is going faster. Okay. That's the end of this lesson. You can use conservation of kinetic energy to solve some problems in a way that's quite a bit easier than if you had to use Newton's laws.